an apology or a mea culpa. I actually miscorrected a misprint. Ugh. Error upon error. So at the top of page 17, we had this vector L. What was L? Look back at our diagram of the cylinder. L was the core of the cylinder. And in the notes, it's written as C2 minus C2. That's obviously not much use. It's just 0. It's not useful for anything. L is supposed to be this vector joining the two ends of the cylinder. Now, the confusion was caused by because I was a bit caught by surprise, and I couldn't work out because there's two choices for the core. You could either have C2 minus C1 or C1 minus C2. It's the two cores pointing in opposite directions from the one end point of the cylinder to the other one. And I tried to look ahead and see which one we needed, and I think I corrected it. I told you in the lecture it was C1 minus C2, but it's not. It is C2 minus C1. So this needs to be corrected to C2 minus C1. There. Now you can understand that. This is good just to clarify the role of these things. What did we, when we set up here the vector equation for the cylinder, this was R equals C1 plus lambda times L plus Q. And now what's going on there? This is supposed to be an equation for a position vector R of a point on the curved surface of the cylinder. And it gets you from the origin to a point on the curved surface of the cylinder in 3 steps. You first go along C1, you then go a certain distance, lambda, along L, and then you go along Q. If you look back to the diagram to see what those were, so the origin is down here. You come from the origin along the vector C1, that takes you to C1, and you're then going to go some amount along the vector L. So we need the vector L to be pointing from C1 to C2. Okay, and the vector, which goes from a starting point to an ending point, it's the position vector of the ending point minus the position vector of the first point. That's the way vector addition is. So L, so for that reason, you see, I see clearly now, I missaw it last week, that L is C2 minus C2. Q was a radial vector, a vector of magnitude equal to the radius of the cylinder, and its direction was left unspecified for the moment. The direction could be anywhere perpendicular to the core. So you get from here, the origin to this point on the surface by going along C1, a certain amount along the core, vector L, and then popping out along one of the radial directions from the core to the surface of the cylinder. Okay? Q makes a right angle with L. Okay. So we worked through that at the end of last week's session, and then there was an example there to find the intersection of a line with the cylinder. So how do people? Do you want to take a few moments to work on that? Now I'll go around answer any questions people might have, and we'll check our solution using MATLAB. And just in the meantime, I'll just while I'm going around, I'll just start up MATLAB as well. Okay, it gives you a chance to ask any queries you have from the stuff we've considered so far as well. And when we've dealt with this example, we'll move on to the rest of Chapter 3. If you have brought your own laptop or computer, you want to get MATLAB out, by all means. Oh my God. So it's example 3.2. Feel free to ask any questions you have or any clarification you'd like. Given the cylinder there, you're given the start point, you're given the velocity vector. The question is the object, is the projectile moving from that point along that velocity vector, is it going to hit the cylinder? And if it does, when? So we did the long general analysis last week, so solution is embodied in the quadratic. You just have to construct the quadratic. It's given there in terms of vectors G and F. G and F are various kind of combinations of the P and the L and the C1 and so on. Then you also have to consider the parameter lambda as well. Actually, it's probably a bit of a long calculation to do by hand. Let's see if we can get the quadratic out at least. You then have to see whether lambda is between 0 and 1. Lambda being between 0 and 1, if you look back at the diagram, that means you stay within that cylinder depicted there. If you go 0 times L, you remain at C1 before you hop out along Q. If you go 1 times L, you get up as far up as C2. If you go outside of lambda between 0 and 1, you're going to be outside that cylinder. You're going to be on the extended cylinder. But if we want to just talk about that finite cylinder, we need to consider the parameter lambda as well. So actually, you may just get to constructing the quadratic. Then we'll have a look at its solution. Okay, I'll just start on that. There we go. You got any questions? Also prepared or brought along one of last year's exam questions. We could also look at that as well. First question just dealing with vectors and various vector problems. I guess the same. Yeah. I did. You got any questions there on the assignment either? Oh, sorry. Here.
You got the, okay, so you said everything you're specifying. So. Now, there's a whole lot of messing around with all these vectors. Yeah. What we were constructing, that's okay. What we were arriving at was this quadratic equation. See, it's quadratic equation with something times t squared times t is constant. We recognize that. Given this dot product, G are specified. They're just introduced shorthand. These combinations, P minus C1 minus complicated multiple of L and G with B minus this. So these F and G are specified in terms of L C2 minus C1. C1 will be the origin. It's not the one. So the L is the core vector. C2 minus C1. That's you've got your L and you've got your P. The initial form of the vector. Well, quadratic is in terms of F and G. F and G are in terms of and arrive at F and G. Okay.
Any queries about any of the vector arguments so far? You know, you could use this opportunity to ask me for clarification on those as well. No, you can't find lambda first because lambda involves t. T's the time at which the integration happens. So you have to find t first. Once you find t, you can go back and examine lambda. Lambda represents. So lambda represents. So here, this point here. Okay, you can get to that point of the intersection by dropping the lambda. But it hits the cylinder when it's also a pointing cylinder. The points in the surface of the cylinder on each side.
No. And then you have to count
The origin is C1. Okay, so this cylinder happens to be positioned in our okay. L is the core vector. So lambda is the proportion of the percent to the average to get to that point. To get to that point on the core, and then you pop out along the radius from the core. So the way the thing works is you said these two, this is the description. Squash those together. This stuff is all part of it. So you to obtain
Well, Q probably not. Isn't something that's going to define it. It's a bit unspecified. Q, so that's just possibilities.
Yeah, that's why.
Yeah, yeah, yeah. So Q appears. Appears in this initial equation. So one of the steps we do is we take the dot product of both sides. And that's everything to do because the ladder is down. But what happens to Q? Do L dot Q. Just zero. Q is the radial vector is directly the course perpendicular to it.
Yeah.
L dot Q is going to be zero. So there's a little bit of a trick, or it's a way of getting rid of this unspecified IQ.
Yeah.
It disappears from the equation. I mean, its influence is still there.
Yeah.
Because it was there originally. The specific directions used, all the circles start using directions. That one feature in these derived we can obtain it, we can identify, once we have the time of intersection.
Yeah.
We got the time of intersection, we work out the coordinates. And once you know X, you know the point R, and you know C. Okay. Yep. This is a dot product. The scalar product of the two vectors. I guess. I mean, you don't have all the privilege stuff just there. You immediately
Yeah. Well,
that's your name that. You should work towards it. Yeah. Well, what's the thing that's doing the multiplication? So what is it that's multiplying? The ratio to the dot product to vectors. Yeah. Once you obtain this fraction, you can right? Yeah, that's scale.
Now we use more.
How would I put it there? Generally, they because eventually, because that was describing the same or
I just left it.
It's not needed.
Such a big.
I'm doing that. Yeah, they're not.
36.
So this is here.
5. Get 46.
I'm almost doing that.
Get minus
I've got a really, it's really rough. I can't be right.
Just retail 27. And you do this when you remove scanning. Well, she's got something else to improve.
So now we get What's the secret in that?
So it's like, here's the air. And it is moving through the air.
It's not like that. You simplify it.
So your walls the floor is also. How fast is it? You get like, you know, we've got L at the end of the F.
That's that by minus, you'll still have your minus 10.
Yeah, minus 9 over minus 6.
Minus 1. Yeah, yes.
So what we're doing here. Well, how facilitating on the
So we're gonna have to work out change
I guess you could like.
Once you get some numbers of G, equation of G. We have 3,153.46.
It's not that possible. You gotta do that. Let's take it away.
Well, started in the first degree. That's what I'm going. The Express. One-way ticket, please. I'm not the Express is allowed because I've got still the 3,103 ones, that actually is not really 3,103. You got to be talastic. You get 3,000. 3,000 minus 6,000. What? Yeah.
Get, so what were people's denominators and G's? Denominators in the coefficients of G? 46, 23, 46. Yeah. Well, it's 83.7.
Let's take that.
Well, obtaining the time t, so you actually have to add.
Second one, wait,
Yeah.
so did you get minus 10? You get minus 105.
Oh, yeah.
Minus 105. Yeah.
Well, remember, what you're trying to do is you're trying to find the intersection points. You're trying to find the time.
Minus 10, take away minus 1. Minus 9.
Oh, shit, that's how you take away. That's nice.
Just taking it in.
Yes. Not equal like 1.
So I've seen a few people with their F's and their G's. So we could check those out. It's an awful lot easier with MATLAB, with any kind of computer. So I can give it the C1, the C2, and the P and the V.
Oh, yeah, yeah.
So what is G? You look at the instruction of G. G is V minus the dot product of... Oh, I need to form L first. So L is C2 minus C1. I can form that easily enough. So G comes out as those values. So you've got positive, negative, negative. Yeah. 180, negative 90, negative 20 approximately. F is minus 8, 4, half, approximately. Very approximately.
What do you have G like? You did G. One take that on like the symbols. 8, 3, 4, 7. 8, 3, 4, 7. Yeah.
Because most people, I think, have F and G out. And once we have those, then we can pass to the quadratic in equation 3.3 on page 18. And you can literally just type it in to MATLAB. So it's G dot G by T squared plus 2 times the dot product of F with G times T plus the dot product of F with itself minus R squared, and I've typed in R equals 2 already. And that's equals 0. When you're typing an equation into MATLAB, an equation in, the equal sign is a double equals. So that says what quadratic is. Ooh, undefined. Yes, you need to define t as a symbolic variable. Then you can define the quadratic. Because t was a symbolic variable, it then goes with symbolic integers. So it keeps the exact fractions. So you've got so quadratic is an equation we can then solve. Now you might hate me now because Killian maybe work it all out by hand. I could have just seen a computer, but I think a lot of you were doing what you were doing with there was like understanding the vector constructions again. That's part of the thing. So I think it's been beneficial for you to interrogate the equations and what does L mean, what does C1 mean, etc., and find it all out. Oh my God. So because it was dealing with a symbolic variable, it kept the quadratic as a symbolic equation. It's giving me symbolic solutions as real integers and square. You can see it's got to the power of half, it's got the square roots in there. So it's not actually evaluating them. So I'll store, but we can get at the actual values by, there's lots of ways. We can store the solution in sol. So sol is it's It's a column vector of two things because it's a quadratic, so it has two solutions, of course. And you can see what the actual values are. The double command takes a symbolic thing and gives you the floating point version of it. So one of the solutions is 0.0345. And we can go double sol 2. That will be the second solution for t, so 0.05. So is there a collision between the particle and the cylinder? Yeah. Because the earlier t value, 0.03, it is less than the bound. We were given the bound of the simulation here is a tenth of a second. Well, this collision is happening before then. So there's, in the calculation of the current frame of this simulation, if you like, the collision is going to happen. So if it's a game or something, it will produce the effect of the collision for the next frame. It will initiate the explosion sequence or whatever is the desired effect of the collision. So the thing to the thing to get from that is how you pass from the original description of the problem, the cylinder, the initial point, the velocity, how that all gets analyzed to produce the quadratic equation. So it produces the quadratic equation there with coefficients given by f and t, but f and t were those f and g and dot products amongst them. They gave you the coefficients, but f and g came from the original setup of the problem. Okay. Of course, we should check the lambda, shouldn't we? That's the other thing. All this analysis has done is found an intersection of the line with the cylinder, but there was a parameter lambda in there which measured how far along the core vector L you traveled, but potentially that L could be any positive number or negative number. So actually, all we can say so far is we've detected a collision with the line and the infinitely extended cylinder. But the question is, well, is the intersection happening between C1 and strictly between C1 and C2? Okay, because this will be some kind of object in the virtual environment. So that comes down to the parameter lambda, which is the proportion of L you move along to get from the end C1 to the point on the core opposite the point on the surface of the cylinder. But lambda, you see, once you know T, one of the equations we passed through was this equation here for lambda. Again, it's a dot product construction using L, P, and C1 and V, but and the T is in there as well. Scalar T multiplied by this dot product. So that can be checked as well for these values of T. So you can check that quickly in MATLAB by just doing a quick function. You can do these anonymous functions. You do ampersand T. It's a function of T, and the function it's this ratio of dot products. It's the dot product of L with P plus V star T minus C1. And that's divided by the dot product of L with itself. I got my brackets wrong. Incorrectly, possibly unbalanced brackets. Dot. My brackets are okay. Dot P plus V, dot L minus L. Did I mean that? Oh, I did mean that. Yeah. Oh, that's really good. It corrected it for me. I didn't balance my brackets, and it gave me, it said, did you mean that? And yeah, so I just pressed enter that. So this sets up a quick anonymous a function called lambda, which takes a value of T and evaluates this dot product there, or this ratio of dot products. So that's just that's the equation for lambda given in the middle of page 17. So we can check that now on Sol 1. Which was the earlier time? The earlier time was 0.03. That was Sol 1, 0.0345. So we can check lambda on Sol 1. Oh, but Sol 1 was a symbolic thing, so it's giving us back the symbolic answer, but we don't want that. We want the double of it to see the decimal version of it, the floating point representation of it. So we get 0.13. That's our value of lambda for that t value. So that is indeed between 0 and 1. So that does represent some proportion along the vector L from the endpoint C1. Okay, so that is a collision between the object and the curved surface of the cylinder. Okay, you could check the Sol 2 as well. Take double of lambda of Sol 2, and again you get 0.58. So it enters the cylinder and it exits the cylinder, the actual finite cylinder segment that we set up, okay? Because both the lambda values are between 0 and 1. Okay. Just zoom this up a bit. So using MooPad within MATLAB, this is a nice way of plotting cylinders and so on. So I can get it to plot the cylinder quickly. There's a plot command which is called cylinder. And to plot cylinder, you give it the radius, the starting point, which was the origin, and the end point, which was 361. So that's the cylinder we're talking about. And we can add into this plot, we can plot the line. It's going to be a three-dimensional line. And you specify a line just by giving the start point and an end point. The start point of the line was minus 10, 0, 0. And the end point, well, I can think of the end point as the initial point plus a little bit of the velocity vector. So I'll go plus 3 times the velocity vector, or plus, I'll just go plus 1 times the velocity vector. The velocity vector was 250, 50, and 1. It's too much of the line. It's made the cylinder very small. Of course, these were happening. So this multiple of the velocity vector, so I've got a 0.1 now. That's like the time value. The two intersection times were less than 0.01. So you can see how here that plot does agree with the analysis that we found. So we did find the intersection of the line with the cylinder. The lambda values checked out as they were both between 0 and 1, so the intersection points are both in the cylinder segment. They're not on the extended cylinder that carries on either side of our cylinder segment. Okay, we could actually just confirm the intersection points as well, because we could add in a point. How do I continue the line? I don't want it to wrap around. So I can do plot 3D point, just give it some coordinates, and of course the coordinates, because I know the t value now, so it'll be the starting point plus 0.0345, wasn't it, times the velocity vector, 250, 51. Yeah. So you can see the dot there. Can you see that on the graph? It's a little bit indistinct on the. Yeah, you can just see it sticking out there. The black dot that it's plotted just at the intersection point of the line with the cylinder. Okay. So it does. Our analysis does check out. If I added in another of those, yeah, you can see it sticking up there. If I added in another of these 0.3D constructions with the other t value, 0.0 whatever it was, 5 or whatever, that would be the exit point. Okay. Any queries or questions coming from that? So we can, we derived this formula. So if you like, the intersection test is solving the quadratic equation in T. And that was the right kind of thing to expect, because a line moving towards a cylinder has to have the possibility of two intersections, an entry point and an exit point. So it seems right that we got a quadratic. And the quadratic came from the analysis of the geometry. So the coefficients of the quadratic are all specified by the vectors. The vector information in the setup of the problem. Okay. So any questions based on that? So I think we may just consider the last case then, done in chapter 3. And so we've done a line and cylinder, and then a line and a capsule. What have we done so far? We've done line and sphere. We've just considered line and cylinder. So then remember, we talked about a capsule as a bounding region. Capsule is a kind of fundamental kind of object. The capsule was a cylinder with spherical ends. So in our diagram of the human figure back here, so we were approximating the limbs as capsules. So they're cylindrical objects with spherical ends. Okay. So if we're trying to figure out an intersection of a projectile moving on a linear path with a capsule, well, we just have to do a number of tests. Okay. So the capsule is the cylinder with spherical ends. You just have to test for an intersection of the line with the curved surface of the cylinder, which is the example we've just been looking at, and also the two spherical ends. Okay, so you'll get a bunch of t values, perhaps, for those intersections if they happen at all, and then by comparing the t values, you can find the earliest one. And that's going to be the first intersection, so that's going to be the collision that happens in the environment. Okay. If you were to think of it as a bullet or a laser or something that's going to pass completely through the object, then you might also make use of the other intersection times, as the exit points, and you'd want to animate those. But if it's going to be a collision which is going to have some effect, like the breaking apart of something, then you just want to isolate that earliest time, and that signifies the actual collision in the virtual environment, which the simulation then handles accordingly with whatever the desired effect is. Okay. So we got a collection of intersection problems there for the linear trajectory with either the curved surface or either of the spherical ends. So before we break, we'll look at this last intersection problem, which is a sphere and a plane. So you'll recall last week, wasn't it, we had a screenshot from the Tomb Raider game. We had the gorilla holding up a big rock, and he was going to throw this towards Lara Croft, right? And we had there, we indicated in the diagram that the rock would have it was roughly spherical shape. So we have a sphere as the bounding body of the rock. And the ground is represented as a plane, okay? So if the simulation is simulating this rock moving through the air towards the ground, we need to be able to detect when and where the collision between a sphere and the plane is going to happen. Okay? So being able to solve that problem of when a sphere impacts a plane, that's a kind of very fundamental collision scenario in the simulation of any environment. Okay? So it can stand for a kind of rough object hitting the wall, or hitting the ground, or hitting the planar surface of anything, hitting a building. Okay? So sphere colliding with the plane. Maybe I should be tougher. Maybe I should set this as an exercise or something. No, maybe I'll do that with. Maybe I'll do that with next year's students. But let's just talk through the discovery of the collision test. Can we say, are we heading towards a quadratic equation in T that we're going to try and solve? It's a bit harder. I mean, if you think of just the abstract object of a sphere moving towards a plane, what happens? If it is going to collide with the plane, it's going to collide with it in some instance. So there'll be one point of intersection between the surface of the sphere and the plane. Because if you let the sphere continue moving, it's going to move through the plane. So then there's a whole, at each frame, there's a whole circle's worth of intersection between the plane and the sphere. When the sphere is kind of halfway through the plane, if you look at what the common points between the plane and the sphere are, there'll be a circle of them. Yeah. No, possibly more general, possibly an ellipse. If the sphere is if its sphere is heading towards the plane perpendicularly, the intersection will always be a circle. But if it's hitting it at the angles that are not perpendicular, then you'll have a more general kind of shape, an ellipse. I think you like that word. Or will it just always be a circle? Well, I think it'll always just be a circle, won't it? Sphere, if you cut a sphere. Oh, my brain. Whatever way you cut a sphere, it's a circle. What am I thinking? I'm thinking of cutting a cone. If you have a cone and you cut the cone with a plane, if you have a cone, so think with a circular base and it comes to a point, and you cut it with a plane, if you cut it horizontally, you have circular intersections. If you cut it at an angle, you have elliptical intersections. But if you cut a sphere, you just think of having an orange and cutting it. Whatever way you cut it, and you look at it, it's going to be a circle. Yeah. So, sorry, I went mad for a minute there. So we are circles. So we'll have a point of intersection, an initial point, colliding point. It'll grow to a circle. When the plane is when the sphere is halfway through, it'll be the largest circle, and then it'll start shrinking again, and finally disappear to a point as the sphere loses contact with the plane on the other side. So that's the kind of thing we're heading for. So it'll be like an interval of values of t. Whatever object we're going to end up solving, it should perhaps be satisfied by an interval of values of t. It's the first contact time, and it's always intersecting as it passes through, and then it loses contact. So that's the kind of rough object. So maybe we're not just expecting a simple quadratic. Okay, so we got a setup depicted in figure 3.5. Where's that? Sphere? No, it's down here. Sphere heading towards a plane. Of course, just drawn simply here as a circle heading towards a line. But you have to think more generally in terms of sphere heading towards a plane. So think of the plane as being fixed. So what do you need to specify the plane? I was talking to, yes, one of you about this. One way of specifying the plane is with its normal vector and a reference point. So P is a reference point on the plane, and N is the normal direction of the plane. There's the moving sphere as well. So to describe the moving sphere, we need to locate its center. So C will be the position vector at the center of the sphere. And we're going to send it on a linear trajectory. So we should know some initial location at the center, and we should have a velocity vector for the center. Then we also need to know how big the sphere is, what the radius is. Well, that's a complete setup of the problem, I think. Reference point and normal vector for the plane, initial position vector at the center of the sphere, a velocity vector for the sphere, and a radius for the sphere. All that information specifies the problem. Oh, sorry, I'm all over the place. Sphere and plane. Line in a capsule. Sorry. Sphere in a plane. So suppose the sphere's radius r, the center c, and the sphere is moving with velocity vector b. v towards the plane with normal vector n and position and reference point p. So the center of the sphere is moving, so it's going to be described as c equals q plus tv. So q is going to be some known initial location of the center, and v the velocity vector. So we can describe the center of the sphere as being at the position q plus tv at time t. Now the plane is a vector equation like this. N dot x equals s. So x is standing for a position vector of any point in the plane. N is the normal vector. And s is this constant that's associated to it. So we can calculate s as n dot the reference point p. So the same constant s comes up when you put in, for the vector x, the position point of any point in the plane. So the reference point p is one of those points. So we can put that in and we get the value of s. Now when does a collision occur? Well, a collision occurs, the first contact occurs when the center of the sphere is exactly the radius distance away from the plane. Makes sense? When the center of the sphere is the same distance from the plane, same perpendicular distance from the plane as the radius of the sphere, that's when the surface of the sphere is just touching the plane. Now coming back to this diagram here, what is the distance from the center to the plane? Well, it's this perpendicular line from C down to the plane there. That's the vertical side of a triangle. So we can express that in terms of, if we make use of this, if we make use of the angle theta there as well. What's the hypotenuse of the triangle? The hypotenuse of the triangle is the vector between C and P. So we can use C minus P for that, or P minus C, and take its magnitude. Okay. So the way we do that is if we take, so just by analyzing the triangle, D is the length of that perpendicular vertical side, magnitude of C minus P is the length of the hypotenuse, and then we take cosine of the angle theta, because that angle theta, actually, that's also the angle up. That's also the angle the triangle is making at C, because they're opposite angles, aren't they? So that angle marked theta there is the same as the angle between the vertical side of the triangle and C. So it's the angle the triangle is making at C. So that explains our expression for D at the bottom of page 19. So then we just worry about where where cosine of theta comes from the vectors. Well, cosine of theta arises when you take the dot product of the two vectors at the angle theta. Okay. So the two vectors we can use there is C minus P and N. Okay. So when we take their dot product, we get the cosine of the angle theta coming back. Okay. So we get this expression for the distance C. It's C minus P dot N divided by the magnitude of N. Okay. Magnitude of N comes in there from the dot product. So when we divide out, we'll lose the dot product. So we just have the magnitude of C minus P times cosine of the angle between the vectors, which is the cosine of theta that we need. So we got our D. So we wanted to know when that distance D is equal to R. Okay, so we just set D equals R. So we set D equals to R in this equation, and we replace C with the Q plus VT, the moving center of the sphere. So we do that, we replace R on the left-hand side and have Q plus VT in the place of C. Multiply across by the magnitude of R to get that out of the denominator. We end up with this equation here at the top of the page. Magnitude of N times scalar R equals a dot product Q dot N, another dot product V dot N times T, minus dot product P dot N. Now we're looking at that as an equation for T we want to solve. Well, you can just, it's a completely scalar equation. Get us vectors there, but they all occur either in a magnitude or in a dot product. So really it's just a combination of scalar quantities So you just divide across and shove everything over, and you get t equals that expression there. Now, so there's the value of t. Just work it out. Now, okay, there's one occasion that formula will fail for t. When's that occasion? Don't read the paragraph underneath it, maybe. When does that equation fail for t? V dot n is equal to 0. Because you're dividing by v dot n. Well, you better be sure you're not dividing by 0. Yeah? What is v dot n? In terms of the problem. So I've got the sphere heading towards the plane. N is the normal vector of the plane. Vector coming straight out from the plane. V is the velocity of the thing. So v dot n equals 0. What does that mean? Sorry, say?
Perpendicular.
Perpendicular. So the velocity vector is perpendicular to the normal. So the sphere is moving that way. It's obviously never going to hit the plane, unless it's on the plane to begin with. But if it's not on the plane to begin with, it's moving parallel to the plane. So we don't expect a collision to happen. Okay? It's never getting any nearer to the plane. It's staying at a fixed, constant distance away from the plane. So that expression fails, or would return an error if you tried to do the division by 0. But that exactly matches the case where no collision is expected. So the collision test, might involve a check first of that dot product v dot n. Is your thing moving exactly parallel to the plane? Well, it's never going to collide with it. Okay. So that makes sense. That all fits together. There's another worrying aspect of it, which we need to solve, is that I made an assumption when I drew that diagram. It looks completely general, but there is a decision made. The decision made there, okay, the sphere is moving, the sphere is somewhere, the sphere is moving, okay, that's general. There's a plane, that's general, but I had my normal vector n pointing up there. Now, equally well, the normal vector could have been pointing exactly opposite direction. Because the meaning of the normal vector is it's the perpendicular direction to the plane, but that could be off this, could be coming into the room, or my arm pointing out of it. Okay, so there's two opposite directions. Now I've chosen there, I've depicted it, and that had consequences in how we analyzed the triangle, that the normal vector n was pointing to the side of the plane where the object was, where the spherical object was. And that set up the angle theta there like that. Equally well, n could be pointing down here. So we don't want to make that, we don't want to build that assumption into our model. Okay. Now, it comes out in this angle theta. If n was pointing, so theta is a smallish angle there, which smallish angles have positive cosines, don't they? Angles between 0 and 90, which theta would always be in this picture. This choice of n, theta will always range from 0 up to a maximum of 90 degrees. Those all have positive cosines. If theta was pointing out the opposite direction, the angle between the n vector and the p minus c would be somewhere between 90 and 180. And those angles have negative cosine. So the choice of direction for n, between that direction or that direction, corresponds to the choice of a plus sign or a minus sign against the cosine term. Okay? So that, we can build that in to the equation by introducing this extra factor into the thing up here, which detects which direction the vector n is. And it's minus the sign of v dot n. So minus the sign of something just gives you a plus 1 or a minus 1. Yeah. So sine is a function. Sine is a function which returns minus 1 or plus 1. Minus 1 from a negative quantity, plus 1 from a positive quantity. So I take minus the sign. So I reverse the sign of v dot n. What sign does v dot n have in that picture? So if you position the vectors n and v and you look at the angle between them, you translate the vector v down to the point P, we have a large angle, an angle between 90 and 180 between v and n. So that will return a negative dot product. Because the dot product of V with n will give you the cosine of the angle between them, which will be a negative quantity. It's cosine of a large angle between 90 and 180 has a negative quantity. But it's that picture which produces a negative dot product of V dot n. That's the situation where we want the positive sign here, plus nr. So that's what we analyzed there. So the correct thing to have is minus the sign of V dot n. So now using this correct formula here, it doesn't matter which side n is pointing, because it's built into the equation. This term here, minus the sign of V dot n, that detects which side V is pointing in, and it adjusts the formula accordingly. But it's nice that the adjustment just comes from the data. It's just the opposite sign that V dot n has. If you know V and you know n, you know what V dot n is, you can observe the sign and you can reverse it. So, you know, it's still a formula that depends on the initial setup. You don't need any extra special knowledge. So this will give you a t value, and this is when the sphere is exactly the radial distance away from the plane. That's the exact occasion when t makes contact with the plane. If we hadn't have made that sign adjustment, it explains it there. If we hadn't have made that sign adjustment, and we had n pointing out the opposite direction, then the time value we would get from the equation would still be relevant, but it wouldn't be the time where the sphere collides with the plane. It would be the time where the sphere has passed completely through the plane and loses contact. It'd be the instant where the sphere is just about to lose contact with the plane after moving completely through it, because that's the other occasion when it's of distance exactly the radius from the plane. Okay. So again, we see how the setup of the problem, position of the sphere, how the sphere is moving, the description of the plane, the normal vector, the reference point, analyzed correctly, it all feeds together to produce us a nice equation which we can just compute. Given all these quantities, we can just compute that and we get the time value. That's when the sphere collides with the plane. So that's the underlying mathematics of detecting a collision between a spherical bounding body, and it's, I mean, most objects are roughly spherical. If you take a random object, it's roughly spherical, I guess, with a plane. But it describes quite a range of general situations. So a rock hitting the ground, spherical object hitting the building. You can see how that all requires that fundamental collision problem. So just before the end of the chapter, we've got 3.9 there. Now this is potentially a whole other piece of analysis. When does a capsule hit a plane? Okay, the gorilla chucking the rock is roughly spherical. Okay, a bounding sphere will do there, but what if you're throwing an object which is a bit too different from a sphere? Then you're going to use a capsule as a bounding body, this cylinder with rounded ends. Now, do we need another piece of complicated vector analysis to detect when a capsule hits a plane? Well, no. If you imagine I've got a capsule here, so a cylinder with those rounded spherical ends. Here's a plane at the table. How could it be that that capsule collides with the table? Well, it could certainly hit it if it hit it with one of the spherical ends first, but that's just the collision of a sphere with the plane. Or it could hit it with the other spherical end. And again, that's a collision of the sphere with the plane. Maybe it could come in completely kind of parallel to the plane, and then the cylindrical surface could make contact with the plane. But of course, the moment the cylindrical surface makes contact with the plane, so do one or both of the spherical ends as well. So really, a capsule hitting a plane isn't all that complicated. It's just the same as one or other of its ends hitting the plane. And the ends are spheres, and we've just analyzed the problem of a sphere hitting a plane. So the problem of a capsule hitting a plane, you just test the two spheres, and whichever sphere hits it earliest, that's how the capsule collides with the plane. That describes which end hits it. If both spheres hit it at exactly the same time, that's the capsule coming in parallel to the plane and the whole length of the capsule makes contact with the plane at the same instant. But probably it's just going to be one of the ends hitting it. Okay? So that problem is already dealt with, really. We've covered the underlying mathematics of the collision of a capsule with a plane. Okay, it's 3:20, so I think that's a place to pause.